All right, so let's look at then, let's jump to the forces now. I have, I think, a couple of more problems to go. And yeah, that should give you, at least, 30, 40 minutes to work on the problem, on the practice exam. All right, so to move a large crate across a rough floor, you push on it with a force F at an angle of 21 degrees below the horizontal, as shown in the picture, and also I have the free body diagram next to that. So we want to find then the force necessary to start the crate moving, given that the mass of the crate is 32 kilograms and the coefficient of static friction between the crate and the floor is 0.57. Okay, then we want to find the acceleration of the crate if the applied force is 330 newtons and the coefficient of kinetic friction is 0.45. All right, so let's for now kind of like ignore the part B. Let's concentrate on part A. Now, remember, when it says rough surface, right, that means the floor is rough. That means you are dealing with the, with friction. There is friction on the surface. So taking this to be your object, so this is your object. What you have here is, that there's a normal force, there's a gravity. Now this person is pushes, there's going to be friction. And you can translate that into free body diagram. So free body diagram takes then this to be your coordinate system. You can take this as a positive X. This is positive Y. Your object is at the center of your coordinate system, and you do the free body diagram, right? Remember, this is N, which is a normal force. You can do capital N or lowercase n, doesn't matter. So N represents normal force. So what you have here is normal force is up, gravity or weight down. Static friction will be to the left because, that box is being pushed to the right. But here's the thing, it's being pushed 21 degrees below the horizontal. So that's translated into something like this, where this theta is 21 degrees. Okay. And our goal will be to basically find what force do we need in order to make it move. Okay. Remember, we kind of talked about this yesterday. So how would I know how much force do I need in order to make this box move or the crate? What information do I need? So basically, if I know one thing, then I can know how much to push. So what is that one thing information? What is that one information?
The X component of the force applied.
Yes, but how strong should it be?
Oh, more so than the static friction.
Exactly. That means what I want to know here is what is the maximum static friction, right? What is the maximum value of the static friction? That means, remember, static friction is an adjustable force. I can push, it can push back. I can push a little harder, it can push back a little harder. And it can basically adjust itself and match my applied force up to a certain point though, right? Up to a certain strength. It can only go as high as basically the surface-surface interaction allows it to. That means what I need to do here is I need to find this information. What is my maximum static friction? Remember, this is equal to the coefficient of static friction times normal force. Okay, that means what I need to do here is, because I already know my coefficient of static friction, I need to know what a normal force is. Once I have the normal force, I can plug in, I can calculate, then I can know how much should be the component. All right. So let's then let's go and calculate this. All right. So it's not it's a medium level difficulty to a little bit, a little bit harder level difficulty. So, but hopefully, you'll be able to follow everything that we talked about. I'm going to go to the next slide over here. And I'm going to again, draw this coordinate system, basically do the free body diagram. Remember, I always have this 4-step problem, right? So 4 steps to solve this problem. Here's my object. All right, so then what I have here is normal force, gravitational force. You can put W or F of G. I like to put f of g. And obviously then we have a friction, static friction right now. And then the applied force, right? You're pushing, but we're not pushing horizontally. We're pushing 21 degrees below the horizontal like this. This is theta of 21 degrees. So then this is our applied force. It's like FP. All right, so next, this is step one, right? Then step two, remember, we'll be putting everything in a table like this. All right, so I have my applied force, Fp. I have my normal force. I have my static friction. And I have my gravitational force. Remember, the net force is the sum of all of them, but I cannot add them all as vectors because they're, in multiple dimensions. So I have to take into account what I want to do is basically find the x and y component of the net force. Okay. So the idea here is that let's treat initially that even up to the maximum value, it doesn't move. Remember, so that means I can say that net force in both directions is 0. Because like that, I can find my maximum static friction force. So in that case, I can see that, all right, so let's look at each force as a vector and in terms of their direction and things like that. Remember, this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And to remind you that it's important to also remember the sign of the values, right? So remember, positive x, positive y, negative x, positive y for the components. Negative x, negative y, positive x.
Positive and negative.
Now, in which quadrant is the applied force, the push force?
Fourth quadrant.
Quadrant 4. So then I know then its x component should be positive, y component should be negative. But then how should I write those components? How would I represent those components? Remember, we need to like break it down into components, right?
You need the applied force to find the x force. You need to find the cosine of the applied force by the angle.
Exactly. See, this is the applied forces x component, and that's the adjacent of that triangle, right? You can see that's adjacent side. That means this becomes Fp cosine of theta, which means the other one is an Fp sine of theta. Once you figure out first one, the second one is just the opposite. You cannot have two cosines or two sines. The components always, one is cosine, one is sine, or one is sine, the other one, always opposite. And then as we said, fourth quadrant, so those are the signs. All right, normal force doesn't have any x component acting in a positive y direction, straight up. Friction is acting in a negative x direction, has no y component. And the gravity acting in a negative y component, no x component. So those are basically my forces in their, with respect to their correct directions. Okay. Now let's then take this information and put it in a step 3 where I set up my equations. In an x direction, then I have Fp cosine theta minus static friction equals 0. Right. Then for the equation 2, then I have normal force minus Fp sine of theta minus gravitational force, which I can just write mg, equals 0. Now, what I have from here is that both of my equations, I end up with a 0 because I have, that's right, we are looking at still in equilibrium position. And what we're trying to do here is we're trying to find, let's go back. Just right, it says, find the force necessary to start the crate moving, given that we have 32 kilograms, so we have the mass. And if you have the mass, that means you can then calculate the gravitational force. Again, go ahead and remind me how to find the gravitational force here.
Mass times acceleration, or mass times gravity.
Exactly. That means this is the, because the gravitational force is straight down and there's no incline, the gravitational force doesn't have any components. It's just basically mass, which is 32 kilograms times 9.8. And we can just basically go ahead and calculate that. All right, so let's do that quickly. All right, so I get 314 newtons. Okay, so 314 newtons. Okay, so that means right now I have the gravitational force. So just 314, just in case if I don't forget that. Sometimes I'm just, so 314 newtons. All right, so then what I have here is I can go back to equation 2, and I can see that what I want here is normal force equals to then Fp sine of theta plus mg. So that's the equation for the normal force. So that's the equation for normal force. But I can't solve for the normal force right now. I know this right here. I know that term, which is 314 newtons. I know what my sine of theta is technically because I have theta, but I don't know what f of p is. We're not given. That's what we're trying to find. What is f of p? Well, same thing with equation 1. If I'm looking at equation 1, and what I have here is this, right? F of p, then cosine of theta equals f of s. But I can see that right now, this f of s, as I said, right, it's mu s times normal force. But still, right now, what I have here is I don't have normal force. I don't have f of s. That means I have, at this point, two unknowns, right? Normal force and f of p. But here's the thing. We have two equations, two unknowns, and we can then combine them to solve for that, right? So we can actually find a way to solve for this particular unknown. Because if I continue this, so f of p cosine theta equals, then I have mu s times n, and I can take this n and plug in, instead of n, I can plug in what n is equals to, which is fp sine of theta plus mg. So what I'm doing, I'm kind of eliminating and combining together, and you can see right now, once I kind of distribute this, which is fp cosine theta equal, then this becomes mu s fp sine of theta, then plus mu s times mg. All I have here is the only unknown in this particular equation. Let's call this equation 3, which is the combined equation. The only unknown is f of p. I have here and there, but that's the only unknown in this equation. That means I can kind of combine them together a little bit, right? I can combine them and solve for the unknown. So that's why this is a little bit harder problem where you have to do a little bit more manipulation, but it's still something that you can more or less be able to do because I have two terms with f of p, so you move both of them in the same side. So for example, we have then fp cosine theta. You move this term to the other side, so it becomes negative mu s fp sine theta. This is equals to then mu s mg. All right. Okay, so the next step will be now I have two things on the left side that include f of p. So I will just factor out f of p.
I have a question. Well, more like a clarification, right? So,
Right.
we used equation 2 to give n a value, right? So the n value was fp sine theta plus mg, right?
Mhm.
And then we use equation, the first equation to, be able to plug in that value because f of s equals, well, friction, static friction equals the mu static times n, right? And then that's
Yes.
how we were able to plug in that equation, right?
Yes.
Okay, sorry. Just
Yeah. So in a way, you could have just go in equation 1 and say this is, for example, fp cosine theta minus. So f of instead of moving f of s to the other side, you could have just left it here. That means you have your original equation 1 and say that this f of s is equals to mu s times normal force, but normal force based on equation 2 is fp sine theta plus mg equals 0, and then just from that just do algebra, right? It's just algebra where you factor out everything. So like, let's say, which basically exactly same thing as I have on this side. That means kind of like this, right? So this equation will basically rearrange itself to be exactly that. Then once I factor out f of p from here, right? Let's actually not, let's not skip a step. So like, let's say when you kind of actually, so let me continue here. Sorry guys, so I'm gonna go from here to there. Then I'm gonna factor out f of p. So if I move up, factor out f of p, then I have cosine theta minus then mu s sine of theta. On the other side, then I have mu s times mg. Okay, and then all I have to do is just divide both sides by what I have in the parentheses. It means f of p equals mu s mg divided by cosine theta minus mu s sine of theta. And you can see, right, this allows me to solve for f of p because I have the mass, I have the coefficient of static friction, and I have the theta. So I should be able to then just plug in everything and calculate. And we should be able to, for example, get 250 newtons. And you can see, right, the normal force is not always equals to mg. Normal force, you have to calculate from this, adding all the vertical forces and components together. And if you have, for example, another vector that has a vertical component or something like that, it also has to be included in this equation 2 of step 3, because you have normal force up, gravity down, but then also have a vertical component of that force, right? In a fourth quadrant means it has a negative vertical component. Anyway, so this particular example, basically, you can just do this and solve for the, applied force. That means applied force, see 250 newtons. That means in a way, what we're saying, because we took into consideration that this is a condition where the object is still at rest, it means this is the maximum force, right? This is the maximum force where my system is still technically then is not able to push the box. but 250 Newton is the maximum force that surface is able to oppose for the box to be moved. So then when I go back to the problem, you will see that in the second part, part B, it says, all right, so now that you know that 250 Newtons is the maximum that friction can oppose, like the maximum strength that it can oppose with. What if we push with a 330 Newtons? Well, we know, right? If we push with 330, it's way above this 250. That means it's more than enough to overcome, the static friction force, and the object will start moving. And then it starts moving. That means we now have acceleration. That means what they have is that if you push with 330 Newton force, you definitely can easily overcome the static friction. Friction doesn't just go away, but if you push much harder than the static friction, then it's definitely going to start moving to the right, being opposed by not static friction now, but kinetic friction. And you can see, right, kinetic friction now has a different coefficient, 0.45, and I can calculate that actually, right? I can calculate this kinetic friction because now that I know my, let's say, applied force, equation 2 that we just had will allow me to calculate the normal force. Because, for example, if I come back over here, see, this is my equation 2 right here. If I know then that this is 330, right? And this is same 21 degrees. And then this is, we calculated as 314 Newtons, which is the weight. I can solve for normal force right away. Because if I have the strength, because in the equation 2 doesn't change anymore. Equation 2 doesn't change in any way because you can see, right, object is on the horizontal axis. If you apply, stronger than the static friction, it will always only accelerate in the x direction. So in a y direction, those forces still going to be balance each other, because you don't assume that pushing the box along the surface, it's suddenly going to start accelerating up or into the floor, right? It's always going to accelerate across the floor. So this equation 2, that means this part of the equation, right, will always be still 0. What's not 0 anymore, equation 1. Equation 1, now you're dealing with the kinetic friction, but they no longer balance because now you're going to have mass times acceleration. This is the Newton's second law. Net force equals mass times acceleration. All right, so let me kind of quickly get rid of this. It's not very quick, but all right, so for example, I can use this to calculate normal force, 330 times sine of 21, then plus 314, I get 432. That means my normal force is 432 Newtons. If I have that normal force, I can then calculate the kinetic friction, because kinetic friction equals coefficient of kinetic friction times normal force. And kinetic friction coefficient was 0.45. That means this is 0.45 times 432 Newtons. All right, I get 195. That means you can see, right, before the static friction was 230 or something, 250, but kinetic only can go as high as 195 because it's always going to be less than static friction. All right, but if I have this, then I can say then FP cosine theta, which is the x component of the applied force, now is 330 cosine of 21 And that's 308 newtons. That means the X component of the push force, where the push itself is 330, but its X component is only 308. But now what I have here is in the X direction, you have then this 308 Newton pushing to the right, and it's opposed by 195 Newtons of friction, which is basically this equation. And this is equals to mass times acceleration, where mass here was, I forgot, sorry, what was the mass? 32 kilograms. Mass here is 32 kilograms, 10 times acceleration. As you can see, right, the only thing I don't have is the acceleration. So 308 minus 195. On the left side, I have 113 newtons. That's my net force, equals 32 times A. Then A here is equals to 113 newtons over 32 kilograms. And acceleration is 3.5 meters per second squared. There you go. All right, so a little bit on the harder side, as I mentioned, right? But as long as you're able to follow this, let's say, and follow the steps, the free body diagram, equations, and things like that, you might not be, you might not see something as complicated as this on the exam, but you will see something basically, slightly easier, but in a similar, similar problem like this. Okay. Any questions on this? I think I have one more problem, but what I have with this problem is a little bit simpler. The idea here is, I never talked about yesterday the spring force. There's also another force that if you have a spring, if you compress or stretch the spring, there's always a force coming from the spring that we call a restoring force. Let's call this restoring force. So let's say you have a spring. So the spring generally, when it's not stretched or compressed, then we can say that it's sitting in its equilibrium. So this is like its equilibrium. That means imagine a spring that has not been compressed or has not been stretched. But one of the things we have is that whenever you compress or stretch a spring, it always, right? You stretch it, you let go, it goes back to its original shape. You compress, you let go, it goes back to its original shape. That's because there's a force, restoring force, sometimes we call spring force, that always acting on the object. That means if I take this and kind of like stretch it to some distance x, there will be force acting, let's put like FSP, spring force, that will always be in the direction of the equilibrium and will always be equals to K, which is some kind of what we call a spring constant. Then times position x. That's the equation for the spring force. All right. That means the magnitude of the spring force. Generally, there's also a negative sign over there, which indicates that if you move the spring to the right, force will be to the left. But if you take the spring with respect to equilibrium, if you compress it, that means you move it to the left, the force will be to the right. So if displacement is to the left, force is to the right. If displacement is to the right, force is to the left. And the reason is because a spring force always points toward this equilibrium position. See, if you move if you compress to the left, the equilibrium on the other side, so the force will be toward that direction. You stretch it to the right, force is to the left because equilibrium is on the left side. Okay. That's basically the spring force. That means you always have the spring force, and this K has a unit of newtons per meters, and generally it represents the stiffness of the spring, just like mu s or mu k represents the the information about the surface. Now, let's look at this example. So let's say a spring with a force of constant of 120 newtons per meters, which basically gives you the K for the spring that we're using, is used to push a 0.27 kilogram block of wood against a wall as shown in the picture there. So what we want to do, we want to find the maximum compression of the spring needed to keep the block from falling, given that the coefficient of static friction between the block and the wall is 0.46. All right, so we'll just look at that part. Now, this is one of those, imagine, we can see in the picture, right? You basically take the spring and push it into the wall. So basically you provide this force over there, where action reaction then, well, there's a wall, the wall pushes back, right? So that means there's a normal force from the wall in opposite direction. Now, the wooden block has gravity acting on it downward. See, the normal force now, a horizontal force. The normal force right now is a horizontal force. But what happens here is the gravity now balanced by the static friction. That's why things on the wall don't slide down because of the friction. Okay. That means what you have here is your force table is, so let's say there's a spring force to the right. So let me do spring force, static friction, normal force, and gravity. Okay. And your system is all in equilibrium, so there is no motion. So you're holding it. This is to the right, the spring force. It has no y component. Static friction now is in a positive y direction. You can see, right, it's upward. Normal force is in a negative x direction because it's pointing to the left, as you can see from here. And the gravity is acting, always straight down. Okay. So that's what you have. So that means you then end up with two equations. Spring force minus normal force equals 0. And equation 2, static friction minus mg equals 0. Okay. Now, what we want to do here is we want to find what is the minimum compression. Now, I don't see any compression information in this equation unless you remember that spring force is equals to that. That means equation 1 is technically is negative kx minus mg equals 0. So that's what we have for this. Okay. All right. So then from that, you can see, right? If you are kind of looking at in terms of the x, you just solve for that because you're given k, you're given mass. That means you can say then k is equals to mg over x. So basically, oh, sorry, we are solving for x. So I kind of like rearrange it. Kx equals basically, in terms of magnitude, they're equal to one another. That means this is the spring force equals to the gravitational force. Then I just divide both sides by k. So you can solve for x. That means mass of 0.27 times 9.8, then divided by 120 Newton per meters. And you can then solve for the x. All right, so I get 0.22 meters, which is about 22 centimeters. If you compress it by 22 centimeters, it will hold the book.